So you have a differential equation, dy dx equals 2x minus y. So you've got your derivative or slopes in terms of the x and y coordinates. So the first thing we want to do is we want to make a slope field, and then we need to sketch a solution curve that passes through the point 0, 1. So we might be able to go point by point here, and we'll just do that because there's only, 12 points here, and it won't be too taxing, I think, to do that. So for example, if you plug in the origin, dy dx equals 0, so we get a horizontal tangent there. Also, when you plug in the point 1, comma 2, that produces a derivative equal to 0. So let's sketch horizontal tangents there. If you plug in the point 1, comma 1, the slope is 1. So I'm going to do a slope of 1 there. If you plug in 0, 1, the slope is negative 1. If you plug in negative 1, comma 0, the slope is negative 2. Negative 1, comma 1 gives a slope of negative 3, so something maybe a little steeper. And then negative 1, 2 gives a slope of negative 4. So anything like that is fine. 0, 2 gives a slope of negative 2, so something plausible like that. 1, 0 gives a slope of 2. 2, 0 gives a slope of 4. 2, 1 gives a slope of 3. And 2, 2 gives a slope of 2. So you don't have to be perfect, but that's, I think, good enough. I think the key thing is you definitely want to make sure you get those horizontal tangents for sure. And then the solution the solution curve that passes through 0, 1 has got to go through this point, go through that point there, and follow the basically sort of follow the the trajectory here, or the gradient. So something like this will be fine. Okay. But in any case, part B was what a student had a question on. The solution curve that passes through the point 0, 1 has a local minimum at this x value. So notice that x value, I mean ln of 1.5 should be some number less than 1. So, with that in mind, maybe I should have made my curve go a little bit lower than 1. We're talking about x values. This is some number a little bit less than 1, so it's plausible, right? Like x equals ln of 2 is apparently here, or ln of 3 halves, rather. Okay, and we want the y coordinate. So the key is that we know that a function has a local min when dy dx equals 0, right, or a critical point. So dy dx equals 0 implies that 2x minus y equals 0, or in other words, the y coordinate is twice the x coordinate at a local min. But we know that this min has an x coordinate of ln of 3 halves, so that means that the y coordinate at the min is equal to, so when x equals ln of 3 halves, we see that y equals 2 times ln of 3 halves. Okay, so in other words, our y coordinate is equal to 2 ln of 3 over 2. Okay, hopefully that helped.